Hey there, so I was recently designing a storage system for a self-sustaining Nether Tree Farm, and I needed a way to extract a precise number of warp blocks from this item stream, done in the most compact way possible. I originally had this dropper circuit here, but it output 9,000 items an hour, which was too fast for the 6,000 an hour that I needed to keep the farm self-sustaining. Now, I could just reduce the speed the dropper gets powered at, but that would require making a larger and laggier redstone clock. So instead, I thought about designing a passive system that doesn't even require any extra blocks. What I did was first swap out the dropper for a dispenser, and then pre-fill some of the slots of the dispenser with a dummy item that the dispenser can fail to eject, such as bone meal or shears. Then, this way, every few cycles the system wouldn't output an item and its speed would decrease to less than 9,000 items an hour. But how much less? Well, that's what I decided to figure out. So this fascinating dispenser math emerges from some interesting behavior with how a dispenser with items going in and out of it fills up over time, given it has a few dummy items in it. For example, say we fill up our dispenser with shears in 3 of the slots. Then, as we start feeding in warp blocks at hopper speed of 8 game ticks, initially the chance of a warp block being ejected is only 1 in 4, so they aren't ejected faster than they feed in. But then, the warp blocks begin to fill up another slot. Now the chance of them being ejected rises to 2 in 5. But then once they start to fill up the 3rd slot, something different begins to happen. Since now half the slots are warp blocks, there's a 1 in 2 chance of them being ejected every 4 game ticks. And seeing as one warp block is fed in every 8 game ticks, the rate at which warp blocks flow in and out of the dispenser equalizes. And the same thing happens if you start with 6 slots filled with warp blocks. Initially, there's a high chance of the warp blocks being ejected, meaning the output speed is higher than the input speed. And then eventually, when the warp blocks drop down to 3 slots, it equalizes again. So you're probably wondering by now, where does the differential part of differential dispensers come from? And my answer to you is this equation right here. This here is a separable first-order differential equation that relates the amount of slots in our dispenser filled with input item I, which in our case is warp blocks, with the time measured in game ticks, t. What this equation tells us is that for each increment in time, dt, or each time the dispenser gets powered, the corresponding increment in I, which is di, is equal to the ratio of the flow of items out of and into the dispenser, subtracted by the chance of our item I being ejected from the dispenser. So in my case, I have a hopper that feeds in items every 8 game ticks, and a dispenser that is clocked at 4 game ticks, so our input period would be 8 and our output period would be 4. Now you might be wondering if the stack size of an item affects this equation. And it does, but in a way in which we can completely ignore. Why can we do this? Well, if for example we have 30 warp blocks in a slot, and as one time interval passes, an item from this stack is shot out, well, let's see what changed in that period of time. We still have the same amount of slots filled with warp blocks, meaning our item output chance hasn't changed. In fact, this chance only changes when a slot is either filled with one item that gets ejected, or has one item that feeds into an empty slot. In either of these two scenarios, there is a change in the amount of slots filled with our input item, and hence the only time the output probability of our dispenser changes is when we're on the boundary of a stack of items, and hence we can disregard everything in between. The only impact having a larger stack size has on our dispenser is that it's going to take a lot longer to reach the equilibrium point. But once we get there, it's going to be a lot more stable compared to if we had an unstackable item. Okay, so this equation is cool and all, but in its current form, it only tells us what occurs on the micro scale of one dispenser cycle, rather than on a macro scale as we run this system for hours on end. To convert this equation to something more useful, we will need to solve the differential equation by rearranging and then integrating both sides to try and get I in terms of t. First of all, I'm going to rename our input and output variables to be more concise. Then, to set up our integral, we can combine the fraction and move it to the left-hand side, so all of our I values are on one side, and then add in our bounds, where A represents the amount of slots that initially filled up with our input item at time equals 0. Integrating from here is relatively straightforward. First, using a bit of algebra, we can get the same coefficients for I on both halves of the fraction, and then we can split the fraction to cancel the I from the numerator, getting the integrand into a form where we can use standard integrals to integrate it. Then finally, we can integrate both sides. After plugging in the bounds and simplifying, we get a nifty expression that implicitly defines the amount of slots filled with our input item over time, given a few constant values. Now, to find the equilibrium point I was talking about earlier, where the number of slots filled up by the input item begins to equalize, we can take the limit of the above implicit function as it approaches infinity. To do this, we can somewhat informally construct this silly looking expression where we can cancel quite a lot of terms, until we get down to just the inner log expression. Here we can exponentiate and reciprocate both sides to deal with that off-putting infinity symbol. And lastly, we can wipe away the absolute value sign and the denominator to end up with this nice expression. Remember that this limit, let's call it L, describes the amount of slots our input stream of items fills up once it reaches the equilibrium point. Something we must do before moving on though, is restrict the value of this limit so it can't go higher than the amount of non-empty slots in the dispenser, given by 9 minus d. To add this restriction, we can just use a minimum value function comparing our limit and 9 minus d. We can then plug L into our formula that describes the chance a selected item is ejected to find the chance of our input item being ejected as the dispenser reaches its equilibrium point. Then we can take this chance and multiply it by the amount of times our dispenser cycles an hour, which is given by the amount of ticks in an hour, 72,000, divided by the period of when we power it, which is p. We can then replace L with the expression we found earlier for it, but now we have this yucky fraction with a min value function in the midst of it all. How are we supposed to isolate and solve for d now? Well, with a bit of analysis, the minimum function can be rewritten as this piecewise equation. And then substituting our new piecewise minimum value function into O, we get this clunky expression. But more good news for us is that this greatly simplifies to just this. From here, we can see that we get two expressions that describe our item output each hour, and we can use cases to determine which expression to use. For example, for my storage system, I'm aiming to extract 6,000 items an hour with an item input and output period of 8 game ticks and 4 game ticks respectively. So plugging this into the first equation of our piecewise, we see that 72,000 divided by 8 equals 9,000 an hour, which is not what I'm aiming for. So then we move to case 2, where the condition in the piecewise is not met, meaning that d is equal to this second equation. Here we can simply plug in our desired rates of O equals 6,000 items an hour, and our powering period of p equals 4, and finally solve for d, and we get 6. Wow. And to think there was no other way to find how many dummy items I need to pre-fill the dispenser with. Like, I definitely couldn't have just set up an experiment in game with 9 different dispensers, pre-filled them with all different amounts of dummy items, and then measured their item outputs using carpet mod? Nah. Okay, so I was just reading through the comments, and someone asked... Oh, just give me a minute. Yep. Nearly there. Ah, there it is. What if you have to use the first equation in the piecewise expression? How does that even work? Because we don't even get to find out what d is equal to because of the greater than symbol. So if the condition of O equals 72,000 on f is true, then we just plug in f and p into the inequality, and then we can determine a range of values for d rather than one specific value. A trivial example of this is if you never feed items into the dispenser. In this case, it doesn't matter how many slots you pre-fill with dummy items, the dispenser will still output 0 items an hour. So in both scenarios here, we either find a single value for d or multiple. Either way, we've solved our problem of how many dummy items we need to pre-fill a given dispenser with to produce a desired amount of items per hour. I've actually already made a tool for this over on Desmos, which you can use to either calculate how many items your dispenser will output an hour given initial conditions, or you can set a desired amount of items an hour to output, and then it'll tell you how many slots to pre-fill with dummy items. If I made any mistakes throughout this video, feel free to let me know in the comments below, as there was a wide variety of maths covered in this video, some of which I've only just learned about, so I found it really cool how it just popped up in a literal Minecraft farm I was working on. This video was made to both cover this math, as I don't believe anyone's documented it and modeled this dispenser behavior before, and also to serve as a prerequisite video for the upcoming self-sustaining stem and shroomlight farm using science video, as I just couldn't find room in that video to fit this bit of math in. I hope you guys don't mind that this was a slightly different style of vid to what I usually put out, and thanks for watching.